In today's lesson, we're going to be looking at Boolean Algebra. Hopefully you already know that computers are made up of hundreds of switches that can only be in two states, 0 and 1, are binary values. Well, calculations are actually completed with the use of logic gates. These allow us to manipulate inputs so that we can produce a variety of different outputs, depending on the arrangement of logic gates. Several logic gates can be put together to create circuits, and then we can use these to create complex calculations. The most basic level that we're going to use, we're going to be using the following operations: not, and the exclusive OR. So over the years, electronic engineers have actually designed hardware that can carry out these fundamental logical operations, and this makes up the CPU. First of all, we have the AND gate, sometimes called a conjunction. The output is only going to be true if both A and B are true, otherwise it's going to give a false output. Notice the notation which is highlighted in red. It's like a small hat which represents AND. It looks like the letter A. And the symbol on the right hand side is the symbol used for the shape. Our second logic gate is the OR gate, sometimes called a disjunction. You'll notice the symbol for this is a small V. The symbol on the right is how we represent the gate, and you can see the notation underneath. Now, when we're using this gate, one of the inputs has to be true to make the output true. Otherwise, it's false. It's only false in the state where both outputs are false. Our third gate is the NOT gate. It's called negation. This is when the input is only, when it's true, the output is false. It inverts the input. You can see the symbol is a small triangle, but it also has a small circle at the end of it. This is because the design of the gate. The symbol to represent this when we're writing out logical statements is a small line with a right angle, and you can see that highlighted in red on the screen. And this is the NAND gate, the not and gate. So you can see the symbol here has the small circle at the end of the AND symbol. And we can think of it as it's shown in red on our screen, A and B not. So what we have to think is it's almost the opposite, it's the inverted AND. So all options are going to give true unless both inputs are true. We also have a NOR gate, not OR. Again, similar to the NAND gate, the NOR gate has a small circle at the end of the OR gate. And in red on the screen, you can see the notation that we use for this. Not A or B. And in this case, it's an OR gate inverted. So rather than us having to draw an AND or an OR and then a NOT after it, we can just use those NANDs or NOR gates. So in this case, not A or B would only be true when both the inputs are false. We also have an exclusive OR, XOR gate. It's called exclusive disjunction. We represent this with the OR symbol but a line underneath it. We can also write XOR. Now you'll see this only works when one of the inputs is true. If either both the inputs were true or both the inputs are false, it will give a false reading. And to represent this gate, we use the OR gate, but we put a line behind it as shown on the right hand side of the screen. We can also have an exclusive NOR gate, XNOR. So we can think of it like our XOR gate or exclusive OR that we looked at before, but this time we have a NOT linked to it. So you can see the symbol for this is shown on the right hand side of the screen. It's an OR gate, which is then turned into our XOR with our NOT symbol at the end of it, that small circle. We represent this by three little lines, but sometimes it can be represented by a double arrow, as you can see on the screen on the left hand side. For the XOR, one of the inputs had to be true, but only one of them. Remember, if both were false or both were true, that would give a false reading. Well, this is the inverse of this. So it's only going to be true if either both the inputs are true or both the inputs are false. We sometimes call this the equivalence. Now, before we go any further, we need to think of an order of precedence. When we've got more than one gate together, we need to think about what we're going to do to remove and simplify the expression. And generally speaking, we go through this: brackets, not, NAND, and OR. So here's an example. We've got a truth table here for P equals not A and B. Now this is like a NAND gate, and you should recognise this from a NAND gate as well. So you can see in our truth table we have two inputs, A and B. We then have our output P. But it's much easier to solve this if we can add an extra column. And I always recommend doing this. Even if you think you're an expert at Boolean Algebra, it's very easy to get one value wrong. So we've put a cube in here. We've decided to do A and B to start with. So you can see the third column in our table is A and B. And that gives us a value of 1 only when both the inputs are true. So then, because it's a NOT, we can just invert those values, and you can see the output would be 0, 1, 1, 1. Now this is really telling us that if we had an input of a 1 from A and a 1 from B, it would give us a 0. It's then telling us whatever other state it would be, it would give a true reading. Now remember, a true is like a small bolt of electricity. Here's another example for P equals not A and B. Now, when we think about this, we have to think about the order of precedence. There's no brackets here. So the first thing that we have to do is write not A. So we can think about inverting the values from A before we use our AND gate. Because of the way this is written and the brackets were used in the last one, it almost looks the same as the previous example we did, but this time there's no brackets. So because we've got our not, we have to do the not A first. So here's another example. For P equals A and B or C. Again, it's much easier for us to highlight an output. So in our truth table, we would usually actually count up from 0 to 1. But this time, we've actually got 3 inputs. So you can see the outputs that we have here. And finally, we have 3 logic gates all together. And you can see the steps that we've gone through to try and figure these out. We can actually define problems very much so in algebra, and your experience of programming will show you this. Now, we have to be able to, at A level, consider a problem and turn that into a logical statement. So, for example, students can take computer science at A level if they pass both GCSE maths and computer science. So you can see how we've turned that into a little bit of code. And we can see the real-life Boolean logic in these samples. Now, in your exam, remember, you're going to have to be able to represent these real-life problems in Boolean logic.